So yeah, basically we have modules with behavior inside, like in hardware description language, and you exchange transaction through ports and channels. Your processing is done in SC thread or SC method, depending on what you want to do, and if you want to be able to suspend or not your processing. Also, one capability is that you can mix, in fact, in this environment, models coming from different worlds. So VHDL or Verilog, C also, C++. You can create your own SystemC module from scratch. And for our needs, we need to have also a processor model in our design. The thing is that you have to take care of what you are doing, because if you introduce some RTL models in the system, the simulation speed will be decreased, and the speed of the slowest modules will be the speed of the system. So we did not target that. We really wanted to have something fast to run the stack, because it was some lines of software to run. So this is why we created this platform at what we call the PV level, or it's the programmer's view level. So it was to do a functional verification. So mainly we target this approach, and then later on we move the infrastructure, the bus, from a PV bus to an AXI cycle accurate bus, and we also change our model. The ARM we used was a Cortex R4, and so we moved from the instruction accurate model, which is provided by Coware, to a cycle accurate, and get more details on some subsystem parts. So in fact, why we decided to use Coware? Yeah, we had two approaches possible. So either to start with OSCE or to use an ESL vendors. So basically, we looked to Confluent, Coware, Vast, and so and also Synopsys. And we decided to use Coware because first, it's mature SystemC solution. It's 100% compatible with OSCE. Yeah, I will not go into details concerning the PCT, the platform creator tool, and the SCID tool, but you can ask the guys on the booth, and they will explain and show you that in details. But these tools, I will show you that just after. They are really convenient to set up a platform quickly, and this was the first step for us to be able to set up something quickly. You have also this SCML library, which is a public domain and a worldwide support. Okay, so what is this CML methodology? In fact, it's a C++ library provided by Coware. You have some smart objects in that, like registers bank, smart clocks. You will be able, in fact, to define your SystemC IP in the same way as you do with hardware description language. You will also have a clear split between the behavior implementation, the registers, and eventually the timing that you will introduce in your models later on. So you have the possibility to introduce timing in transactors and such things. Also, you can reach fast simulation speed using this tool set, because you have off-the-shelf some models from ARM. I mean, we use ARM models, but as I told you, we had also these EVP models created for us. The SystemC scheduler is optimized, and at the beginning, when you just want to have all the piece of code into the same environment and not looking to what is happening on the bus, you can bypass the bus exchanges and transaction by using a mechanism which is called a backdoor mechanism. And last point is the debugging capabilities. You have exactly the same debuggers first on your cores that you will use later on your IC. So it means that for ARM, for example, we are using real-view debuggers, but you can also use Lauterbach debuggers, and it is exactly the same environment. So it means that if you are starting to write script to automate some steps, then all this script can be reused later on with the final IC. You also have something which is really fruitful, is the VPA. So it's the Virtual Platform Analyzer. So this stuff will allows you to see all the IPs you have in your systems, to see the registers contents of all the blocks. You can put breakpoints in read and write on registers, and so you can all the time see exactly what is happening in the system. So this can be compared to a GTAG debugger, for example. Yeah.
So you mentioned on here the fast simulation speed.
Yeah.
But one of the other tools you looked at, you said was VAST, and their claim is fast cycle accurate. Obviously, they give up something to be cycle accurate. How did you find the simulation speed compared to a company like that?
I mean, first, yeah.
Maybe to repeat the question.
Yeah. So the question is the difference between Coware and VAST compared on the simulation speed that we can achieve target. I mean, with the core. So yeah, the first answer is why we did not use VAST, because it was not 100 compatible with OSCI. Second point, we did not really check into in detail. I mean, the simulation speed that we can have, but because the cores are coming from ARM, so we expect that the ARM models are the fastest model, in fact. So I don't know if it's really answer your question, but yeah. Okay, so how you will create your system? In fact, so you have the first tool, which is SCID. So it's the development environment. So it's based on the Eclipse framework. So you can for sure use your preferred debugger editor, type your code. But we use quite often this guy. So you will have your C++ code. You have the memory content that can be displayed here. There is also some waveform viewer available. And the local variable also can be seen. What we do not see really here is that you can also see the state of the thread in the system, which one is running on wait and things like that. So basically, you will create your models, then you put the models into a library, and then you use the platform creator, which is this tool. So this tool will allows you to do a drag and drop from first the libraries available from Coware. So you have a set of functional units or IPs already available with this, like a timer, DMA, and things like that, bus. And you will have your library with your IPs. Then you just drag and drop the models into this main window. You do the connection between the blocks. The tool will check for you automatically the connection, and it will produce the top level, in fact.